Okay, welcome to the session. I hope you can hear me well also down there. We're just missing one of the speaker, but I saw him around. So in a few minutes, I hope he will join us. But I think also seeing the time that we can start the session, I would like to welcome you to this session, which is Green Vehicle, Next Generation Electrified Vehicles Optimized for the Infrastructures. And I see Dimos coming, perfect. My name is Guido Sacchetto from European Commission. I'm working in DG Research Innovation, Unit C2, Future Urban Mobility System. Dimos, please, have a seat. Thank you. We're just starting now. Okay, you know how the session is organized, so there will be 4 presentations plus a question and answer session. And please be engaged, check all the presentation, listen to what is said, and ask all the questions that you want to be answered. The speakers are here for that. So all the projects of this session, as you might know, have been funded under the Green Vehicle topic, which is of 2018, Integrated Brand Independent Architecture, Components and System for Next Generation Electrified Vehicles Optimized for the Infrastructures. And the specific challenge that the projects would like to achieve, and we'll see the result this afternoon, is to develop new components, new systems and architecture for the next generation of vehicles in the future. So the focus would be really, and what was asked from the topic, to focus on meeting end-user expectations in terms of cost, of convenience, of traveling, of course, and on comfort, but also finding the best compromise possible between the fast charge, the battery size, and the battery life. Our first speaker will be Florian, just next to me. And, well, before that, let me introduce also Roland, who will take care of the question and answer session. Roland Uerlich is team leader on e-Powertrain at the Institute for Automotive Engineer, the Ika, at Aachen University. And he's also co-leader, together with Ian Fay, that I see down there, of the Pillar 1 Vehicle Technologies and Vehicle Propulsion System for battery electric vehicles and fuel cells electric vehicles for the revision of the 203 that is taking place right now. Another message, please be engaged on that side as well. If you have something, some inputs, we're looking for that. Okay, let's pass directly to the first speaker. As I said, will be Florian Callender. Florian has an academic degrees in both mechatronic and electrical engineering. He works as a project manager, in the research and development department with Infineon Technologies AG. He manages various projects, national and European, in the field of automotive, industrial, and quantum technologies. He will be presenting the project called 1,000 Kilometer Plus, so Scalable, European Powertrain Technologies platform for cost-efficient electric vehicles to connect Europe. For the project, we know that we need to, just maybe a few words on the project. We wanted to see how we can meet the demands of our everyday life. So we will hear about the key technologies that have been developed by this project, and in particular, well, things related to the power technology, the platform, and cost efficiency. Florian, I would like to have you on stage, and the floor is yours. Please, I will ask you, all the speakers, to stay in the 15 minutes. If you hear a bell ringing, it's also to wake you up and to say that the 15 minutes are over. Thank you.
I'm happy to. Oh,
no, it's just you need to click to open the presentation.
Yeah, okay.
That's it, yeah.
Perfect. Thank you. I'm here to present the project 1,000 Kilometer Plus. At the very beginning, I give you a short overview of the project. The project has started in January 2019 with 10 partners, 6 million budget, and the partners are out of 4 countries. And it will end this year in the end of June. And the partners are contributing to our demonstration vehicle, where we want to show a 1,000 kilometers plus car. Infineon is coordinating the project and is responsible in the consortium for the power modules. Mercedes-Benz is responsible for the demonstration vehicle, which is a Mercedes EQC, which is adapted to the project. AVL and Mercedes together, they are for the integration of the final demonstration vehicle responsible, and AVL is also responsible for the thermal management and the energy management. The Fraunhofer IISB Institute takes care of the battery system and the fast charging. Ionity, as a provider of charging infrastructure, is also responsible for the fast charging and for the counterpart. The OTH is responsible for the smart navigation system, because using electric vehicle in our daily routines, you need to have a smart navigation to get the most out of your car, let's say in that way. The University of Brünn is responsible for the algorithmic in the car. Hutchinson takes care of phase-changing material to cover the heat losses during the fast charging. The Technical University Dresden is responsible for the lightweight components used in the car, and Valeo Siemens for the inverter and for the e-motor. In the project, we want to achieve with our demonstration car these objects. We want, the most important is a 1,000 kilometer drive within 12 hours with only 90 minutes of charging time and only 3 charging stops. In the next step, a 2,000 kilometers trip in 24 hours and a 4,500 kilometers trip in 3 days. And we want to demonstrate fast charging in everyday use, realistic driving ranges, cost efficiency, highest electric efficiency, and we want to demonstrate that the results gained in the project can be used for the European mass production capabilities. Our vision is to connect people, economies, technologies on Europe's electrified roads. And we want to integrate a brand-independent architecture, components and systems for next-generation electrified vehicles optimized for the charging infrastructure. The project is divided in 3 supply chains. Supply chain 1 is the high-efficient powertrain. Supply chain 2 is about the fast charging in the battery system. And supply chain 3 is about the energy management, the communication, and the demonstration. In supply chain 1, we build up the powertrain used in the 1,000 kilometer plus demonstration vehicle. It is on 800 volt technology. We use a 3-phase permanent magnet synchronous motor. We use silicon carbide MOSFETs in the power modules, and we use a transmission gearbox with a single single-speed gearbox. As you can see here, I do not know if you can see my point, but on the right-hand side, we have an efficiency for the overall powertrain, which is around 94%. It is the e-motor together with the transmission and the gearbox. In the supply chain 2, which is about the battery system, we build up a battery containing around 80 kilowatt hours of capacity. As mentioned, we are in an 800 volt system. We have around 5,000 battery cells in a serial and parallel configuration. And in addition to this battery system, we... Okay. Okay. In addition to the battery system, we did some research on phase-changing material to take care of the heat generated while the ultra-fast charging. In the supply chain 3, we adapted the software and the thermal management of the vehicle. We took care of the navigation system with a smart navigation system for your final destination that you want to reach with your car. You want to take care of the charging stop. You want to find the most efficient route to the charging stop. And before you do the ultra-fast charging, you want the car to be prepared, to be conditioned for the ultra-fast charging. And this is done with the routing system. And the last thing in this supply chain 3 is the buildup of the demonstration vehicle and the testing of the vehicle. This is the steps we are currently working on. And I can show you a video which shows the build-up process and shows more or less a cool overview of the whole 1,000 kilometer plus project. I think with this video you can get a impression how the project is, what we are doing, what will do the project for the future, what are the impacts of the project. With a 1,000 kilometer plus project, we address challenges that are challenges of today's electric vehicles. These challenges are driving range, charging time, and performance and costs. And with a 1,000 kilometer plus project, we set the foundation to make, by addressing this challenge, to create a European electromobility that meets both the demands of the user and the demands of the market. I'm at the end of my presentation. Thank you very much. If you are interested in more information, feel free to look on our web page or our LinkedIn page, and I'm happy to answer some questions after the other presentations. Thank you very much.
Thanks a lot, Roland, and thanks again also for staying in time. I mean, you also had some additional time, so we're perfectly on time now for the next presentation. Now we move to the second project, which is CEVOLVER, so Connect Electric Vehicles Optimized for Life, Value, Efficiency and Range. The speaker is Dimo Gatidis, and Dimos worked for 10 years as a scientific advisor for members of the German Parliament, as a senior consultant for the German 12 ministries, and also in coordinating pilot projects for the Connecting Europe Facility, the CEF. And today he's head of the government relation in the Research Innovation Department of FEV. He will present the project CEVOLVER, as we said, and this project developed a holistic predictive for energy management and eco-driving that support drive and at an optimal speed profile, increasing thus the efficiency, and also with an optimized size of the battery, so taking into a strong account the user-centric approach that we saw as one of the main focus of the topic. Okay, that's it, and I would say, Dimos, the floor is yours. Thanks.
Thank you very much. Thank you very much for this kind introduction. I have nothing more to say because this is really perfectly summarized. Today I'm replacing, in fact, two technical colleagues of mine. Let's step into the energy and thermal management that we investigated in the CEVOLVER project. CEVOLVER stands for Connected Electric Vehicle Optimized for Life, Value, Efficiency and Range. As already said, we started at 2018, running for almost 5 years. The call and the topic dealt with a BEV, battery electric vehicle, usable for long day trips with an affordable battery. So the main focus is on comfortability and affordability. Requested, less than 2 million euros funding. To make a leap forward in customer acceptance of e-mobility, we take a user-centric approach to identify the pain points of the customers. Today, the only remedy against range anxiety seems to be a large battery, but its costs is prohibitive to many users, at least with public subsidies. But they fear also the small range of a small battery, because they are afraid that they cannot charge the battery when they need. And why is the range indication so confusing? Will they get over the next mountain or not? And how much will the charging delay the travel? We must blast all those bubbles of worry. So we start with increasing the range of the small battery, a holistic predictive energy management and eco-driving that supports to drive an optimal speed profile, increasing the efficiency. The range of the small battery is predicted with high accuracy because our eco-routing includes road grades of 3D maps as well as weather, traffic data from cloud services. So you know when to charge before a hill. Eco-charging enables fast charging with more than 2C. And it has accurate information about charging station that is included in the route planning. User guidance and technology solutions build trust in the vehicle, despite its small battery. And the trust in smaller batteries enables bringing more affordable vehicles to the market. So, in winter, the range of an EV suffers from heating. At -20 degrees, you can expect you spend about a third of the trip energy for heating. To blast that bubble of worry, as promised, thermal management is the key to make the battery energy drive the car farther. The mechatronics system of energy and thermal management, later also in slide 7, appears quite simple, but it already tries to visualize the use of waste heat for cabin heating and a heat pump supporting this. So breaking it down into components, you can see the electric energy paths in green, cabin climatization in gray, and different heat exchangers and so forth. So the user-centric approach of vehicle configuration looks into different use cases. For a passenger car used for commuting or traveling, a heat pump pays off as it is more efficient than a PTC heater. In contrast, the driver of a parcel delivery van, for example, will open the door very often, thereby losing the warm air created by a PTC or heat pump. Here it is better to provide, as shown in the pictures on the right, comfort by heating surfaces that are radiating to the driver or that the driver touches, like, for example, sun, with a dash lower, and so on. So the thermal management also keeps battery temperature in the right window for fast charging. And it recuperates cooling heat for cabin climatization to save energy in the winter. In order to double-check matching the scope of the call, we took a look into the dictionary. The dictionary defines a day trip as a journey in which a person goes to visit a place and then returns home at the same day. Ford's day trip use case for its commercial vehicle is a craftsman's day job. The drive with eco-charging guidance starts in Maasmechelen, Belgium, across the Netherlands, and enters finally Germany. With fast charging 3 times on the way, the commercial vehicle visits the assumed job site near Landau, which is south of Germany. There the vehicle is charged again during the construction job before the return home. By the end of the day, a 700-kilometer trip is completed. On the way back, one fast charging point did not communicate with the vehicle. Losing time on this attempt was the reason why the target of 30 additional minutes travel time on each way was exceeded by a couple of minutes. Using this, our OEM partners completed 700 kilometers day trips, of which I would like to address also the result of Fiat in this presentation. Having understood that fast charging infrastructure is unfortunately not overwhelming in Europe yet, Fiat had to choose the route shown here between Orbassano and Seriale to demonstrate the viability of visiting a family in 350-kilometer distance and going back home again in one day. So the trip from Orbassano to Seriale is almost 180 kilometers, and the trip back 170, 350 kilometers in total, which were done then twice in one day. Compared to unadvised driving, the trip time optimal driving turned out to enable 7.6% energy saving and 9.7% time saving. It is only a paradox at the first glance that adding a charging stop saves time. But instead of charging the battery to 100% with declining power, of course, this helps charging the battery in that SOC window of the maximum C rate possible. So charging time is cut by 47%. When the emphasis was on eco-driving, almost 12% electric energy was saved, but this added a little to the trip time. This, in accordance with the results of the simulation study, this is, of course, in accordance. Further on, coming to the end, we have to discuss especially three aspects: interoperability, motion control, and cloud services. Yeah, this closes my pitch. Thank you very much for listening.
Thanks again, Dimos. Well, we're saving a lot of time for questions, which is a good thing. Okay, thanks again. Now we move to the third project that will be presented. It will be presentation by Thomas Guery. I hope I pronounced it correctly. And Thomas is a senior researcher in the e-power, so efficient power electronics, powertrain, and energy solution research group at the VUB, Mobile Research Center, but I think you know also. And has a strong expertise in power electronics and energy management system. He's also covering, of course, his activities, EU and national projects. He will be presenting ACHILES or ACHILES, I don't know how to prefer to use it. I would say ACHILES. ACHILES, okay, perfect. He will give us some, well, maybe just an outlook of the main outcomes of ACHILES for the deployment of more efficient electrical and electronic control architecture for the next generation of electrified vehicles. And this will be also by four main technology concepts, and correct me if I'm wrong, it will be the new wheel concept design, a centralized computer platform, an out-of-phase control, and the new torque vectoring algorithm. So these are the main four parts that I think will be presented today. Thomas, floor is yours. Thanks.
Thanks a lot for the nice introduction on the project as well, quite complete. So I've been managing and coordinating the project together with Omar Hegazi, also from the VUB in Brussels, not too far from here. So it started in December 2018 and lasted for 48 months instead of the planned 42 months. So 6 months extension due to COVID is still reasonable. And then it ended in the end of November last year, a few months ago, with the final event at the TRA conference. So we had around 5 million euros EU contribution for 10 partners in total. So we were coordinating from the VUB side in Belgium. And then we had different OEMs on all project innovations. Together also with Audi, who was one of the main partners in the project, also providing the baseline vehicle. So maybe I go directly to the main project's objectives. So the main objective was to develop a more efficient EE control system architecture, optimized for the next generation of electric vehicles. And in particular, we aimed at enhancing a baseline Audi Q2 battery electric vehicle. So that was provided directly by Audi on the project. It's a car that's mainly or only available in China, where we implemented all our innovations, which are closely linked to the objectives. So we have 4 main innovations objectives. The first one is the development of a new positive and negative torque vectoring algorithm. So it's aiming at enhancing the dynamics of the vehicle. I will present the results of each of these innovations in the later slides. The second one was to develop a new wheel and e-braking concept, also quite crucial for the vehicle. So we replaced all the wheels and worked on the braking system to reduce particle emissions, to have it more to have it lighter as well. The third one was to develop a new out-of-phase control e-drive to dissipate energy in case of regenerative braking when the battery is fully charged. And the last one was to work on the centralized computer platform, the CCP, that was mainly from our TT Tech partner. Then, with this, we aimed at achieving initially goals on reducing the total cost of ownership, increasing the driving range, and then also the autonomy of the car. So as I said, based on the Audi Q2 battery electric vehicle that we worked on in the project. So results linked to the different objectives, starting with the first one on the torque vectoring. So as I said, it's aiming at improving the dynamics of the car with also improved safety and efficiency. So there were improvements at both component level and system level with the whole driving of the vehicle in the end. And we did many maneuver tests, both with hardware in the loop and in the actual vehicle, showing that there was indeed better cornering behavior. Stability and safety were increased also by more than 10%, with improved understeering and oversteering. So we can see here the torque vectoring that was included into the CCP, the control platform, to have it more centralized, and the hardware in the loop with the simulation platform where we can drive the car and observe all dynamics. And TRL went up to 7 for this specific innovation. The second one on the new wheel and e-braking concept. So that was one of the main innovations, and in the end was a success in the project because we reached a high TRL level. So it works with pure bi-wire braking, so no more need for hydraulic fluids in the transmission from the pedal to the brakes. It's all with electric brake actuators, still fully safe with SLD compliance, so it's a reliable system still. And we had electromechanical brake actuators with aluminum disc rings. So due to the out-of-phase control and reduction in the, due to the out-of-phase control, if we have the batteries fully charged and we want to use regenerative braking, we can dissipate in the e-motors, so we can reduce the friction brakes and use aluminum instead of steel, which we did here, for in the end a weight reduction of approximately 19 kilograms compared to the Audi Q2 battery electric vehicle. Also quite important here, the brake particles. So even though it's a fully electric vehicle, we still have emissions in the brake particles, which were here reduced by 50%, which is quite a good achievement. The third one on the out-of-phase control for the new vehicle architecture. So we have two e-motors that have been developed by our partner Elafé with high heat dissipation capability and high efficiency at low torque as well. So we were able to, as I said in the previous slide, downsize the friction brakes and use aluminum thanks to this out-of-phase control. And each of them can then dissipate 10 kilowatt of power continuously. In case the battery is fully charged, we can still then use regenerative braking, and they're both direct and near wheel electric motors. So you can see them here, while component level in the car as well, up to TRL7. The last one is on the centralized computer platform that was also developed within the project. So the idea was to go, well, from the more decentralized architecture that we have nowadays and in the past, and to go towards a more centralized EE architecture where we integrate different software functions. Here we did that mainly for the torque vectoring that I showed in Innovation 1 and the BMS software unit, which we also worked on in the project. So that was quite a big challenge, because when you start from an existing car to reroute some of the signals to do some reverse engineering in the end was quite a big challenge and took a lot of effort. But with decentralized architecture, we were able to reduce the weight of the vehicle because we have less wiring and harness, less ECUs. So in the centralized platform itself, we have 20% less weight and still easily compliant in terms of reliability, and reduced complexity because we have less controllers. In the end, we have a more centralized architecture. So in the end, results were verified and tested in first a simulation framework that was then taken to hardware in the loop by our project partner Technalia with their Dynacar platform. So we could really work on the model calibration, both in simulation and then hardware in the loop. Also trying to reduce the development time for integration. If you can simulate everything in advance, it really helps in the integration, with testing both at component level and for the full vehicle in the end to assess the performance and calibrate all the models that we have been developing throughout the project. So we have had different calibration phases, and in the end, we could show that the Achilles car weighs less from the different innovations that we have, has also a good efficiency with better dynamics, also reduced costs for the components that have been developed compared to the benchmark that was actually considered in the proposal, a C-segment vehicle. Okay, now a few words on the longer term impacts. So we had good improvements on the e-Powertrain technologies, mainly the e-motors, also with improvements on the efficiency. We had the integration of the different concepts, functionalities into the vehicle. We believe by taking them to a higher TRL level, also working quite a lot on the standardization, how to ease their integration into the market. We can also improve the affordability. These new functionalities, of course, improve the quality of the whole vehicle in the end. And we have considered other aspects such as sustainability, environmental aspects also, and health of the users, with mainly the reduction in the particle emissions. The safety concept of the centralized control architecture, because you need to make sure still it's really secure, fully reliable. That was assessed by an external party, TUV, certification body. So it's still ASIL-D compliance for the innovative components that we have integrated into the vehicle. And we have worked on the market adoption with both the standardization of the different components and also dissemination activities. So we had quite a few in the project, including the final event we had in November last year at the TRA conference in Lisbon. And we participated as well in the EVOLVE cluster with actually two of the other projects here, where we had many joint dissemination activities. So yeah, workshops, conferences, publications as well. So that actually went on for most of the project, and Achilles was leading the cluster up to recently, actually, the end of the project. So now we have one video to close the presentation. So it's a condensed version of the full project video. I thought we wouldn't have time to do the full one, but here is the video.
Since 2018, the Achilles H2020 project partners have been working on developing a more efficient electronic control system architecture for a new generation of electric vehicles. To demonstrate their innovative concepts, they have enhanced an Audi Q2 battery electric vehicle. After prototyping the main components, 2 e-motors, the brake system, the front transmission, the motor controllers, and Dynacar, all Achilles outcomes were tailored to the demonstrator's physical characteristics and fitted into the demonstrator. The final physical testing of the Achilles demonstrator took place and showed promising results. One of the most challenging brake tests, the Großglockner test, executed by Continental and Audi, determined the effects of high thermal stress on brakes, brake pads, and discs. This successful downhill run in the Alps proved that the Achilles brake system is stable. A brake particle emissions test showed a decrease of at least 50% of brake particle emissions stemming from the use of AIMMC brake discs. Fraunhofer LBF coordinated a total of 130 dynamic maneuver tests performed by several project partners to assess the improvement of the Achilles demonstrator vehicle's response. Various improvements compared to the baseline vehicle, in particular with regard to efficiency, have been demonstrated at both component and system level. Final and tested Achilles demo vehicle weighs less, has increased autonomy, and smoother dynamics for an overall lower cost.
Okay, that's all. Thank you, everyone.
Big applause. Thanks again, Thomas. Okay, now we're still good on time. I hope you're still all awake, otherwise I can use my bell to wake you up. Are you still in the room with us? Okay, good. Now we're going to the last presentation of this session, and we'll ask on the stage Theodoros Kalogiannis from VUB to present SELFIE. The project is self-sustained and smart battery thermal management solution for battery electric vehicles. Theodoros has a PhD in energy storage and is currently working as a postdoc senior researcher in VUB, still VUB. His expertise ranges from testing and characterizing battery cells to designing mechanical, thermal, and electrical architecture on multi-cell topologies. He will be presenting his project SELFIE, which is now on the back in the presentation. I hope everything is ready. And the SELFIE is, again, one of the projects that we saw under this call that was funded, the topic 2018, aiming at developing a novel compact battery system. And in particular, it consists of a smart modular battery pack and an advanced thermal management system, which means that these can help and enable fast charging up to 5C, which is a lot, with the strongly reducing the charging time and increasing the energy efficiency, because obviously there should be minimal losses. But I guess Theodoros now will present some of the result. Thanks.
Thanks for the introduction. I hope you can hear me well. I thought that you were going to present, but okay, I will take the speech. So I'm Theodoros. I'm working for VUB. I'm a senior researcher, and SELFIE is one of the projects that we coordinate. My colleague Thomas also saw Achilles. So what we do in VUB, we are working for the full value chain of the battery cells. We have seen many nice presentations today about the battery cells, starting from the future of the batteries, as we see before. I don't know how many of you attended, but you see that there are a lot of challenges on the small power level. So by developing a new battery cell, it is already becoming a challenge. Now we are going to see how we are taking these batteries, how we are upscaling the power and the energy levels to an electric vehicle in order to meet the demands that they addressed in the green vehicle calls, like 1,000 kilometers and fast charging. So what we do in the battery innovation centers, we start from from the material themselves. We can take the materials in the raw form, and we can mix in order to produce the new battery system, the new cells that they can be comprised of NMC, LFP, or different kind of cathodes, but also with new generation 4 or generation 5 with post-lithium ion technologies. Afterwards, we model and we experiment with the battery cells. We also do characterization on commercial battery cells, like the one we used for the SELFIE project. And we develop the models that they are a good representative of the real battery cell. So it's not a physics-based model, because we have to make compromise between computational power and accuracy. As we've seen before, we can make a high fidelity model, but usually for application demands, this is not the case, because it will take ages to converge to a single result. And now we want to see fast what the state of charge or state of health of the battery it is, and then also to take action after we take this result. So in the battery, in our group, in the VUB, we develop the models, but also afterwards we investigate different applications like electric vehicles or energy storage. So in general, we can see that this is the first life of a battery. So if we produce a battery cell, we have the first life, which is up to a certain, let's say, state of health levels. And then we take the battery from this application and we move to the next one, that it's a second life, as it is said. And with the battery passport, we can extract the information in order to track accurately each battery cell and to optimize the performance in the next, let's say, life, the next travel that the battery will do. Usually it is about energy storage, where the requirements are lower than an electric vehicle in the streets. So this is the second life, and we can reach up to a certain state of health. Afterwards, we move to the recyclability. We see different methods in order to take the material from the batteries themselves to extract with regeneration or recycling, and in order to produce new materials out of it, and then to build again the new battery cell with the highest gravimetric or volumetric energies. It was something that I saw before, that already we are reaching 750 or 800 watt-hours per liter for a battery cell. For SELFIE, we are only used 200 maximum in the best case we found that time when we started the project, and this was only 4 years ago. So we see that we are moving very fast the capabilities of the single cell, and by doing this circular economy we can evolve to the next stages. So what is SELFIE, and what we do as a VUB, as Battery Innovation Center in SELFIE? We coordinate, and myself, I'm coordinating the project, but we also have some technical activities. We have some collaborations with 10 partners among the whole Europe, and especially 8 countries. It is a 4 years project in general, and it has some delays. There are some challenges to implement some manufacturing components, and the project will end in July 23. So I don't have a lot of results to show at the end user application at the highest TRL levels, but we can see that we are going towards this direction. It has 8 work packages, and it is approximately 6 million euros. Last but not least, and very importantly, SELFIE is a member of the EVOLVE cluster. EVOLVE cluster is comprised, as Thomas said before, by 8 partners, which brings together as synergies to answer the technical challenges that they are requested in the green vehicle calls. But you can find more details about all of this information, about the SELFIE project, about the EVOLVE cluster and our group in the links shown here. So what is the SELFIE objectives? How this project was generated? As it's stated by its name, it is a self-sustained and smart battery thermal management solution for electric vehicle batteries. And the aim, the overall aim of SELFIE, it is to develop, but also to demonstrate at high TRL levels, a novel and self-sustained compact battery system. And you know that when we are talking about electric vehicles, when we are talking about road transport, the battery system is the most crucial component, one of the most crucial components in the cars. So we want to target it with a smart modular design, and a general advanced solution for the thermal management, not only of the batteries themselves, but also of the cabin, because we want to give the optimization of the performance of the batteries themselves, but also the passengers during the driving experience of the electric vehicle. So we propose a new thermal management solution, and we investigated heat buffer, the so-called phase change materials. This is something really challenging. These materials, they are very, sorry. Yeah, I have to speak faster. We have to use these materials in order to have the perfect interface between the different layers. So we saw before that we have the electrodes. The electrodes, they generate heat. We go from a mono layer, we go to many layers. All this creates extra resistance. And if we go to the system level, you can imagine that the losses are highly. So we have to minimize it in order to reduce the cost. And this is one of the major impact of the SELFIE project. How we achieve the objectives? We have some target achievements in order to meet these objectives. So the first achievement that we have to meet, it is to fast charge up to 5C. So when the project was created and the idea was born, we wanted to reach 5C, and with respect to 10 minutes charging. And bear in mind that we are talking about a 400 volt system. We are not going to 800 volt technologies. So we are really aiming on fast charge with respect to time. We want to have 10 minutes, 15 minutes of a charging, of a full charge of the battery pack. And then we want also, in the same time, to enable a longer range. We need to meet 1,000 kilometers by the request of the call. We want to reduce the overall cost of the pack level by 30% by simplifying the design of the battery pack. As you understood, there are a lot of challenges, and we want to tackle these challenges by reducing the volume and the weight of the full battery car. And then in the end, we want to combine it with the optimal performance of the thermal management of the whole drivetrain by reducing up to 55%, let's say in winter time, the overall cost. These are the achievements. And to achieve these achievements, we have some key innovations that they address here with a novel cooling plate, because there are many solutions in order to cool down, to control thermally a battery cell. Imagine that we have to dissipate the heat as fast as possible. We propose here a cooling plate, a novel cooling plate. Our partners from Fraunhofer, in collaborative manner with all partners consortium, we came to this conclusion. I will show some results in a while. And also we want to use efficient thermal interfaces in order to have rapid heat exchanges, but also to use active battery housing materials. We don't need a housing and enclosure that it is only safe or lightweight. We want also to be able to be thermally optimized in order not to have losses during this approach. And then we need to have it as a modular design in order to be easy to maintain and to upgrade, upscale, or to different applications like Second Life, as I said before. And for doing so, and to optimize the overall control of the cabin and the batteries, we use a phase change materials as a heat buffer solution. Okay, so in the results, what we see here our battery cell in figure 1. It's a typical prismatic battery cell. It's a lithium ion. It's approximately 23 amp hour, and it is around 180 to 200 watt-hour per liter, quite low compared to what we can achieve today. But this cell, when it is under fast charge, we test it up to 8C, but for our application, we wanted to verify with 5C. We dress it, we put an enclosure with different mesh, so we can have aluminum mesh or copper mesh in order to see how the heat is dissipated. We also used heat pipe solutions, another indirect cooling solution that we wanted to see how effective it is. And then we used also, as shown in this part, a hybrid solution a hybrid solution with phase change material together with the aluminum mesh or with liquid cooling. So if you're not familiar with the PCM, it's like a wax. So it has different, let's say, composition if it is hot or cold. And we can take the heat from it depending the energy, the phase change it takes, the transitions. We verified our models with experiments, and in our labs we created high fidelity models to investigate further at the abnormal scenarios and to see which solution we should keep. And based on the manufacturer recommendation, we have to stay between this 30 to 40 degrees optimized range, and we see that the PCM, phase change material, or PCM graphite, it's another, let's say, combination. We can keep at fast charge rate the batteries at a certain level, but this is at the cell level. And then we have to go to a module level. After we selected the optimal solution, we say, okay, we have to go for this battery cell. It is a tailor-made solution with a hybrid approach. And as you see here, we have the aluminum plate, which is empty side, and it is filled with the phase change material. And this also here we can see, barely see anyway, we can see the liquid plate, which is a combination in this figure. This is a module for a proof of concept that we built in our labs with the PCM on the bottom and the hybrid solution, the cooling solution, sorry, in the side of the cells. Also, partners from LBF, they build an innovative compartment to accommodate our batteries and our hybrid, let's say, thermal management. We also investigated novel front earth modules that they are used in order to optimize the heat exchange of the batteries. We integrated the BMS, a partner from Fraunhofer ISB, they developed a new one, validated with thermal solutions, and then partners from Turkey, Imekar, they integrate everything to the battery pack. And afterwards, this is now under testing. Currently, we test this solution that it is everything as a unit. And we see here some results that they indicate the performance improvements of our thermal management. So starting from left to right, we have the time over the temperature evolution. And at this figure, we see how the batteries behave at a modular level without any thermal management. And you can see that if we simply put the batteries inside the electric vehicle, this happened like in generation 1 with Nissan Leaf. If you remember, we have some strange conditions at hot weather. This is what's happening. The temperature is going very high and the batteries either degrade too fast or they can result to thermal runaways. But also, we investigated only with phase change material as a heat buffer, and we saw that we have a 15% improvement in the temperature distribution and the temperature evolution, I'm sorry, and our hybrid final solution can efficiently keep to the range that it is recommended. For now, because we haven't proceeded to the vehicle validations, we see that this solution can serve for 20% cooling power reduction at the vehicle level. Results to be achieved, let's say. We have here a conventional vehicle. It is the Fiat Doblo. This is with internal combustion engine. And what the SELFIE is going to do is going to take the vehicle, remove everything, all technology, and replace it with a new one. And what is the new one is all these components, especially with the battery and the electric motor, and the heat buffer that we proposed in order to achieve the objectives with the key innovations and all the proposed story that we are aiming at. The impact of SELFIE project, it is mostly one of the most impact is to increase the user acceptance. So we want to reduce the overall cost and we want to eliminate the range anxiety. The SELFIE wants to ensure that the batteries, they can withstand the high currents, the fast charging rate, without reducing the lifetime of the batteries. and with the minimal losses. That means that without dropping, let's say, the warranties of the OEMs. And we also see that a 20% improvement can lead to an overall 8% in reduction of the electric vehicle. So we aim to improve the cost, but also the lifetime of the battery cells. Moving towards the highest charging rates with, let's say, 1,000 kilometers with 90-minute pit stops, by using these fast charge techniques, we can see that we can keep the efficiency of the overall efficiency of the drivetrain high without increasing the battery mass. So we see in this figure, this is just a theoretical figure, that the efficiency drops if the battery mass is decreased in order to have high 1,000 kilometer range. But now with the SELFIE project, we want to decrease the battery mass, keep the efficiency high, and also keep the 1,000 kilometers. This is to be evaluated in the future steps. Last but equally important, we aim for the decarbonization of the transportation sector because it has a huge environmental impact, and we want to make it not anymore dependent on the fossil fuels. We want to integrate the innovation and the knowledge between collaborative works, industry, RTOs, and university. And this impacts concludes my presentation today. Thanks for your attention and your participation today.
Applause and thanks again to Theodoros. Well, okay, this full presentation hour over. We can open the table for discussions. We have all the four presenters here next to us. They will be speaking directly from the table. It will be impossible otherwise. I hope you can see it from down there at the end of the room. But please don't be shy and ask the question. It will be Roland that will take care and manage the question and answer session. Thanks. Just one thing. The first question will be a bike ring bell.
Okay, thank you for the kind handing over of the session. First of all, I will give all of you the chance to ask questions, and if then we have some room left, I think Guido and I have some questions as well. But first of all, just feel free to make yourself noticeable for some questions, and yeah, stage is yours.
One full question, I'm sorry, this is the last offer. I will take it. I have a couple of questions, but I see a hand raised down there, and the second down there.
Okay, well, the colleague with the red pullover, I think it was.
This is Pietro Perlo, IFEFS. Indeed, the work you're doing is tremendously important. I was just, yes, this is the reason why I wanted to ask the question. But I will take another one, by the way. In January 2023, so just 1 month ago, Tesla was fined by the Korean authorities, as perhaps you know, because this is public stuff, because their range at minus 15 degrees was 50.5% less than what they claim, okay? And then they made a test of all cars, and they understood that at minus 15, practically all commercial cars today on the road, all, are in between 45 to 50% lower range than what they claim. All, none excluded, okay? There are very nice report. Perhaps you read this report, because this is a public report, no? So now the question is, I didn't see any real implementation of your work, which I repeat is very important, because this is what we have today. At minus 15 degrees, it's 50% less, plus or less all, none excluded, okay? They find the Tesla, but the other are the same level. But this also, there is some 25 to 30% less range at minus 1 to minus 7. There is a very nice report coming from Canada in this direction. So do you have a expectation from your work? Because thermal management, I repeat, what you're doing is very important, but do you have expectation on this as a result of what you're doing at low temperature, not such low, by the way. Okay? We haven't I didn't see any real expectation.
So maybe when one of you wants to answer, otherwise I would maybe hand it to the colleague from the SELFIE project. As you have the heat buffer, you are probably the most likely one to answer.
Yes. Interesting. We had a discussion about it yesterday with one of my colleagues, and he has an electric vehicle, and he told me that he realized that the range drops when it is rainy and not when it's cold to his vehicle, and it is also something strange that it's a parenthesis in this comment, but yeah, low temperature indeed it's affecting a lot the performance of the batteries, and we have seen when we tested single cells that when we go for low temperatures at high fast charge that we want to achieve now, the lifetime is dropping and also the performance is dropping. There are some solutions that they have been investigated at the moment. They are called like preheating techniques in order to reach the temperature at the manufacturer recommendation levels, usually at 20 degrees. But this was not an investigation from the SELFIE point of view. So we were focusing more on the cooling aspects during the warm climates, and we didn't focus on the heating point. But it is a nice, let's say, future work to do with our battery system. Yes.
Okay, maybe another question.
Well, I have a question for the 1,000 kilometer project, the first one. Well, you showed a nice picture of and some nice numbers of the battery system with, let's say, impressive number of cells in series. I think in the order of 200. Did you make any estimation of what is the reliability of such a long string of batteries?
Actually not. Yeah, we focused not in the project. We did not focus on the on the lifetime and the reliability of these cells, because battery was the battery system itself was a research topic, but not the batteries used in the car. We expect with a high power charging and with the battery system that we have, after our tests, we will have losses in the capacity, in the health of the battery. But actually, this is something we did not investigate in the project.
Okay, well, if that's sufficient for you as an answer. Otherwise,
well, maybe I would add something more.
We
yes.
have something to add. Yeah.
But, do you plan to do something on that in the future, or you have any idea, suggestion, or some thoughts? I mean, just to know, I accept it as an answer, of course, and I love to be sincere and clear, because that's why we're here for, to understand what we're doing and why, and if there are some additional points. But from your point of view, is this something that would make sense, and maybe also in, I don't know, if in Infineon Technologies, you're doing something on that side, or you know of somebody who's doing and working in that direction?
Yeah, there are investigations going on. Infineon is doing some investigations regarding monitoring state of charge, state of health of the batteries with certain methods. Our partner Fraunhofer, who did most of the research regarding the battery system, did test bench tests regarding the reliability of the battery. But this is something where I'm not a technical expert in, and I can't give a clear answer. I'm sorry for that.
Excellent, absolutely.
No. We speak with microphone only, Pietro. Otherwise, people online, they cannot hear you.
Okay, but maybe another technical question first. So I have just Well, if somebody else wants, yeah, perfectly.
Just, I think two of you used phase change materials inside. Do you know something about market implementation? Is it used on the market as well? So the nice thing now is in parallel, e-mobility goes up. Everyone knows now charging and whatever and rain but the phase change materials could help. Is it implemented?
It's not. Can you hear me? Okay. Yes. It's not implemented yet in the OEMs with the OEMs, but it is still under investigation because there are many challenges with the weight, but also with safety point of view, because it is liquid, so and it has some conductivity, electrical conductivity. So in case of it can create some let's say unsafe scenarios for the battery pack. Yeah, and this is actually a challenge that we have with our projects, because it is difficult to manufacture an aluminum plate and actually to weld it and shield it in order not the liquid to pass from inside to the outside. So again, mechanical engineering, but it's everywhere, yes. And it was difficult to preserve because we have different layers inside the battery pack. We had a sandwich approach, so we have some cells on the bottom, we have the PCM plate, and then we have another layer of battery cells. So it is not possible to guarantee at the moment that the PCM plate of aluminum plus PCM, it will keep the liquid at the liquid form inside safely. We have, for instance, with the same pilot line, we have 1 out of 6 plates that it was defected, and it was creating some challenges there that we didn't realize in the beginning. Yeah. I think this drives some OEMs to not to use it at the moment. Yeah. In our group, we have used also a different type of solution. So this is a hybrid plate, but actually the liquid channels with the PCMs, they are not interacted. We have also constructed with another manufacturer a PCM plate that it has the coolant paths from inside. So it's actually one plate that it has integrated the PCM and the coolant. And also in that case, it was the same problem. The water glycol was mixing with the coolant, with the PCM itself, and eventually the pipes would have some error. So I'm just a researcher, but I think in the OEMs maybe they have the similar issues, and still it's not in the market. Yeah, maybe near future. Yeah.
Thank you for the answer. Maybe just one follow-up question, as we also did some project with PCM materials. Just when you compare your solution with the second plate for the PCM under the battery tray, when you compare it to a normal thermal management with a heat pump and so on, how is it compared in weight? So how much do we add compared to a normal battery system?
Yes, the weight it is increased indeed compared to another solution like with air or only liquid. But in total, we can reach higher C rates, and we actually didn't look on the capacity itself in the SELFIE, but how to charge faster the same capacity. So we excluded somehow the weight of the equation in this direction. Yeah, but indeed it's much heavier. Maybe this is another reason that we don't go to.
Thanks a lot.
Yeah.
Maybe some other questions.
Hello, my name is Janis Humor from LS. I have a question for the Thomas from the ACHILES. I see that he's a little bit bored here about the discussion only about the batteries. First question would be, what is actually the overall efficiency of the electric vehicles? Where is the biggest potential to improve the efficiency? And then the second question would be, you were speaking about also the recuperation. What is actually the efficiency of this recuperation, and what can be done to improve this perhaps even more? And then the second question would be, okay, again regarding the battery, we were speaking so much about the fast charging, very fast charging, but in the practice, this is leading us all to use the electric vehicles the same way we are using now the ICE vehicles. But the general idea would be, that we would use electric vehicles differently. That means that we would charge slowly and controllably every time that vehicle stops, and also by using, of course, the V2G technology. But are these two different types of charging, let's say the fast charging and on the other side V2G and slow charging, are there any contradiction regarding how the batteries are designed, how the batteries are managed? Because we would really like to slow down the life and also leave the vehicles to charge slowly. Okay, so that means those two questions.
Three questions. Okay, yeah, maybe on the last one first. So we did not directly consider the charging in ACHILES, but I think this V2G, different types of charging, smart charging management, it's all coming into place now. But I think the management on the battery side needs to be handled as well. It's sometimes considered in the smart charging, like how do you affect the state of the battery if you charge faster for some other reason, which is the other negative effect that you have on the battery, and this is considered in the balance. How that's considered, maybe Theo can comment on that, but I think it's starting to be taken into account also in the different charging strategies that considered V2G, fast charging, or a slower one. Second question on maybe first on the efficiency of the vehicle. So actually we noticed, because we tried to work a lot on the efficiency in ACHILES, and we noticed that it's a big challenge because most of the losses in the vehicle actually come from the drag losses, so the aerodynamic resistance from the vehicle. And that it was really not part of the project. It's also maybe harder to work on, or there are more limitation, but that's really more on the design of the mechanical design of the vehicle. So even trying to really improve the efficiency of the powertrain, efficiency of the e-motors, we really had marginal gains on the overall vehicle efficiency. So that's why the actual compared to the baseline ODQ2, our ACHILES car has very slightly improved the efficiency. However, even with all our innovations, improvements we made in the car, we are still, I think, around 15% better than the C segment benchmark vehicles that we had considered initially in the proposal. And second question on the regenerative braking. I think maybe the way to improve it is, again, the impact it has on the battery, because even in the initial car where there was no out-of-phase control to dissipate in the e-motors, there were some braking resistors that would dissipate the heat. There was the heavier and bigger friction brake as well. But the current that you put into the battery was not really controlled or limited or whatever. So it's maybe that you have, depending on how you control it, also a negative impact on the battery. In our case, we were able to dissipate the energy, remove the braking resistors, and reduce the friction brake. But still, the current that you put on the battery was not really limited. So that may also be something to consider. Depending on how it's aging, its very specific characteristics, you need to also pay attention to that. So maybe that would be an improvement for the future.
Have you perhaps considered adding for the regenerative braking for the high currents to add supercapacitor, to store this excess of energy in these short times?
I don't have the numbers in. That could be an option. I don't have the numbers in mind of how much we had to dissipate, or how much we could store. But we need to check which are the possibilities indeed.
Okay, we have another question far in the back.
Thank you, Maurizio Maggiore. I would like to sort of link some of the questions with something in the presentations. I think one of the projects mentioned. Yeah. Okay. Yeah. 5C in order to have basically a fast trip without the penalty. Now, maybe starting with a 30 kilowatt is a bit small, but I would just ask, given also the innovation on the phase change and the other cooling materials, to me, and maybe answering also the question about the weight. Today, many cars have a 60 kilowatt hours battery and an 80 kilowatt hours battery with something like 5 to 10,000 euros of difference. So would you, well, first of all, where are you with demonstrating that? Because that was in the targets, but then I'm not sure where, let's say, what has been demonstrated there. And second, with such a charging, done not, of course, every day, because that's not the purpose. The purpose is to allow someone to buy a 50, 60 kilowatt hours battery and still do fast enough a long trip a few times in a year. If he's doing long trips every day, maybe then he needs the 80 kilowatt hours battery. But what is the balance there? I mean, 60 to 80 kilowatt hours, for instance, is a certain different weight. Is the cooling offsetting it or not? I mean, is there consideration of this type in the projects you've done? Because at the moment, I think it's a little bit in the air. We don't see the results. The cooling is allowing this, and are there other solutions that would allow this kind of trade-off? Because in terms of cost and in terms of weight, I think is what we're looking for. And if it is 40 kilowatt hours, better.
Yes, I think this is addressed for SELFIE. Indeed, it is true that not every day we have to do this 1,000 kilometers, and maybe today it's a bit outdated. The technology has went beyond us while we were trying to reach this goal with the new chemistries and the new cooling solutions perhaps that they do exist. I would say that if I understand correctly the question about the demonstration, that it still needs to be verified. So we are running some challenges with the integration into the changing from the conventional internal conventional combustion engine to the electric vehicle, and we are going to run the different scenarios in order to validate our assumptions. But so far we can only estimate that we can achieve this goal. Yeah, I see you.
Microphone. No, Maurizio. Yeah. You need to speak in a microphone because everything is recorded and people's watching online. Otherwise, they will never understand us.
Yeah, that was another thing that came to my mind. Why did you start with a combustion vehicle when you could have modified any of the existing electric vehicles? And if you have difficulties, why don't you do that? Simply.
Yes, this I'm afraid I cannot answer this question because I joined the project after this decision was made, but I can only assume that the idea was to keep the technology that the OEM has for the chassis, everything that they had at the moment, and simply translate it to the new energy storage, to the new solution. But this is my assumption. I cannot verify this. And to go to a new electric vehicle, of course, now we have other vehicles that we can take, but it will require new designs of our full project, of the compartments of the battery pack, of the thermal control. So I don't know if the mechanical design can fit to another solution. But Of course, it remains to be seen. Soon we will have the results and we can have a concrete, let's say, conclusions on these points of view. They are very valid, and I also consider this.
Okay, thank you. But I think we had first one question here on the front.
Can I
I will just one.
Well, I've seen some also through the question some let's say concern about efficiency, round trip, energy recuperation, etc., etc. And some of the projects are targeting an increase of efficiency of I don't know, because there were no numbers. But anyway, are we really concerned about the efficiency of an electric vehicle and improving the efficiency from 94 to 96%? Does it really make the difference when on the other side the efficiency was 20 to 40%? Wouldn't be instead the point that we thought about, let's say, it from a general point of view, like it was stated about the battery. So, how we are able to make the battery big and scalable to the different needs, and on the other side, because we are on the vehicle side, and therefore there is we see it from the vehicle side. How the infrastructure, so how the smart grid is part of the game of this trip, because all the projects see it from the point of view of the vehicle, but on the other side there is the supply.
Yeah, maybe I can start at least on the first part. So indeed, as I've mentioned before, yeah, the efficiency of the vehicle is really challenging to address and to improve, because most of the losses come from drag losses. That's why at least in ACHILES, our main focus was really on developing all our innovations while keeping a similar or slightly improved efficiency with regard to the initial vehicle that we were working on, still improved compared to the old one. So I would say now with the new electric vehicles that have really high efficiency, it's becoming less and less of a concern. Now it's more how, based on a certain battery capacity, how do you manage the range that you have? Can you work with a lighter vehicle depending on the application, depending on the charging infrastructure that's in place? How do you use the battery also to improve the lifetime of the battery? In terms of efficiency, maybe it's less of a concern nowadays with the new vehicles. And on the charging infrastructure, so that was indeed not at all considered here, but it's really major points. I think there are specific calls for that, and it's for more than sure that it's coming together with the. I think most of the technology is ready now. It's more a matter of financing the charging points, planning the installation, planning the arrangements of the electricity grids accordingly. Maybe some user impact or user acceptance that needs to be tackled as well. So it's maybe everything that comes around the actual technology, because the technology is there, but now we need to plan the installation, acceptance, and how we can have it fit also with the different batteries, because we need to see which is the charging rate of the batteries, because we want to have fast chargers, but then that has an impact on the battery of the vehicle, so that has to be considered jointly as well.
Maybe a follow-up question from my side. I think in the CEVOLVER project we had seen some results regarding the routing of the vehicle, at least for the demonstration routes. I think there was one kind of issue with the charging exactly. How do you see kind of the impact of the smart route of eco-routing for such vehicles in comparison to the battery size?
In comparison to the battery size, unfortunately, I can't answer that because especially that technical colleague just left the room 1 minute ago. But perhaps another point concerning the connectivity issues and cloud services and all those business case related new aspects related to the charging. Let me put it that way. If you think about the anxiety, the range anxiety, and all those discussions also about charging anxiety, we really need soon, I think, some kind of charging summit where those questions could be addressed also with other stakeholders who could fully and technically brilliant could answer questions to cloud services. I mean, to be honest, we are not as experts in each and every field. We need to stand together and we need to talk on a regular basis together, and also with the politics together, with the petrol station operators, the housing industry, the parking space companies, retailers, network operators, municipalities, because anxiety as a social phenomenon and a personal one, if you are on the driver's seat, is a point. And I don't think that it is too far away to think about that when trying to answer your question.
Okay, thank you. I think we have another question in the back.
Yes, actually, on the road, some 65% of EVs use LFP cells. The rest is NMC. There are two different worlds when talking about thermal management. If you have LFP, cooling is not so important. Heating is important. If you have NMC, and if you live in a hot country, a good part of your energy is used to keep the battery at the right temperature working properly. I did not see in your evaluation any consideration one chemistry to the other. They are two totally different worlds. You cannot start making a thermal analysis if you do not explain first what kind of batteries do you have. I repeat, LFP cells need to be heated more than cooled, because at 50 degrees they work very well. NMC cell at 50 degrees are died. Not died, but so you have two different worlds. You have to treat the two type of EVs in a completely different manner. Otherwise, all these analyses have no value. Excuse me for my consideration.
Yes, this is true. Actually, at the beginning of the project, we analyzed it's not one NMC, but many NMCs, and not only one NMC with graphite, but NMC with titanium anode. And actually, we concluded is that we want to have fast charge rate, and at the time, NMC couldn't deliver this without LTO as an anode. That's why we choose this cell in order to realize the project that it was already born at that stage. And the LFP, it was also a solution, but it was not as feasible because of, how to put it, economic reasons. And we couldn't find the proper, let's say, battery manufacturers to supply these cells to us. We would have a different study case, of course, with an LFP, but to start the project efficiently and to provide these different solutions for fast charge, we selected these cells. Of course, the LFP can deliver the same fast charge rates, but it was another reason not to go with this chemistry. We have some projects running right now at VUB that we're comparing different chemistries, and we see the performance at different, let's say, conditions like C rates, temperature, or different agings, depth of discharges, and everything. So we can have these conclusions, but not in the framework of the SELFIE. It is something different, I would say. But I totally agree with your concerns. Yes.
Maybe again a follow-up question from my side. In the SELF project, you talked about 5C, 6C, somewhat in that area. When comparing that to the extra benefit that you get from charging with such a high C rate, comparing to the battery durability on the other side, what's your opinion on that for the user actually? Is that such a benefit that in the end you will switch for that higher C rates, but your battery being earlier at the end of life?
Yes, indeed. Lifetime was again one aspect that we couldn't include in the SELFIE framework, but we expect, based on other, let's say, activities, that by keeping the temperature at the normal recommended range window between 25 to 35, we can expand the lifetime of the battery cells.
Thank you. Maybe some more questions from the audience?
Came to my mind about skills. How many PhDs did you educate in your project? Since you are at the end and we have years of skills, do you know how many new PhDs we have thanks to this project?
I'm not 100% sure. I think 2, but I'm really not sure.
Yeah, from our side it's 2 in average as well, but only from our university. So other partners, yeah, I'm not sure because it was mainly OEMs also, so I think not too many PhDs from their side.
In our project, it's also, I think, 2.
Yeah, and for us also it's 2 from standard number.
So another questions, otherwise we have someone in front.
But I have a question. I don't know if it's the case. Also to hear Florian, it's something that I was thinking before and I was expecting somebody to raise this question, but maybe I'll ask it to you. Your project is focused on really a high-class vehicle, no? And I was thinking, okay, you're achieving a 20% cost reduction on that, but how scalable is it, the kind of solution that you demonstrate? Is it something that can be better exploited, also expanded to other categories and sectional vehicles or not?
Absolutely, and this is a question. Electromobility should be affordable for everyday use, and we use a Mercedes EQC vehicle in our project. Yeah, of course, Mercedes is partner in our consortium, but this question, absolutely, this can be reduced and this can be scaled. You have to start new technologies you started at some point, and usually you do not start it in the low class. I do not want to say low class and high class, but is the opposite. And you need to access the market. And with the EQC from Mercedes, we had a platform where we can play around with, where we have a battery system that we can adapt with, where we had 2 different powertrains where we can move one out and change the other one. And with the technology we developed, for instance, we have a 200 kilowatt motor. This is very, very high, but you can scale it down. You need to start at one point, and you go to let's say this is the starting point, and of course it is scalable, and it can be used in cheaper vehicles and in different platforms. And I do not know what else to say. This is a reasonable question, but it is the starting point.
Okay, good. Maybe just a follow-up question on the platform. I'm quite curious. So, okay, you're starting from 200 kilowatt down, and what are you expecting to exploit the result with? Is it limited this sector, or with the platform you expect to get some additional scaling up down to 100 kilowatt? I have no idea of what the platform is doing. Any other detail you can share?
Since I'm not working with an OEM, I do not know what is the strategy here. I think from at least in the 1000 kilometer plus project, the idea is to be in that power rating, but to be more efficient, and the power rating to have a 200 kilowatt engine, it comes with a certain efficiency, and if you scale this down to 100 kilowatts, this is possible, but it comes with less efficiency, and this is what I understood from the partners. Now we want to focus the efficiency to make to address the needs of the customers, which is driving range, which is fast charging, and the comfort that comes with combustion engine should be the same as for electric vehicles, and so the efficiency is something why we currently come with this power rating.
Okay, maybe another chance for the audience here. But if that's not the case, I think one question left. Again, for the CEVOLVER colleague, you had just one very specific question, one comparison between the energy management with the heat pump and these PTC heating systems. And you outlined that one is more suitable for the passenger car and one is more suitable for example, a delivery situation. Could you maybe outline the reasoning behind that? Why that is? No, okay.
The short answer is
Yeah, I'm sorry.
and the long answer is no. Not now.
Yeah, maybe later, or you send me to a colleague who can. Okay, so last chance for the audience, I think.
Maybe I'll go on with Thomas, if I can. A question, something, because I think you're the only one focusing on regenerative braking systems. Because I think you did something in the project, if I remember, is one of the four, the full brake-by-wire. That, of course, will become increasingly important in the future. I was reading some of your deliverables, and I saw also, and I noticed some recommendation and suggestion on regulation, how to better approach this. Do you have something you can share, or some ideas that came out from the project on regenerative braking systems for the future?
Yeah, so regenerative braking and by-wire is different. By-wire is the link between the pedal and the brakes, which we made fully electric here with electric brake actuators. On the regenerative braking, yeah, we worked mainly on the out-of-phase control that enables to dissipate in the e-motors when the battery is fully charged. On the brake themselves, yeah, they also enable regenerative braking in the sense that we downsize the friction brakes. And actually the brake systems, they're already quite close to the market. So I think they plan to, go on with putting them on the market shortly, actually, after the end of the project at Continental. I think the main item would be on the standardization. And actually you have, I don't know if it's that one that you read, but you have one deliverable fully focusing on the standardization, how to faster put the components to the market by having standard rules for different types of vehicles, how they can be more easily integrated in different types of vehicles as well. So I think that applies as well to regenerative braking, in the sense the brake system itself in the wheel. Now on the out-of-phase control, I think it's more within the control architecture that it has to be considered. But I think there's no real limitation in the implementation of the control system to enable the regenerative braking.
Maybe I also have a question regarding the braking system. You switched, when I got it right, the SD brakes for aluminum brakes, and you had a reduction in the emissions for the brake system overall, as I guess. But if you compare the discs directly, so the steel and the aluminum discs, at same performance levels, is the emission different, or how different is it actually?
Yeah, so it's reduced indeed by around 50% for two reasons. One of them is that you have aluminum instead of steel. So indeed, that's already one thing. But here we could use it because we had the other phase control that enabled us also to have both aluminum disc and downsize them. And then if you downsize them, of course, you have also lower particle emissions. So these were the two reasons: downsizing and the fact of using aluminum.
Okay.
Yes.
I think we have one question from the audience again.
You mentioned this, I forgot to ask this because you mentioned a point. What is exactly this out-of-phase control? Because this is something quite new in this.
So you have the e-motors in the Powertrain, or in this case they're close to the wheels, but doesn't really matter. So usually they're operated to drive the wheels, and they're operated at their best efficiency. Depending on the load, of course. Here, out-of-phase control, it means that you operate them out of their best efficiency, out of phase, so that you actually you lose energy there, and you can dissipate the energy from the braking. Because when you brake, you need to do something with the energy that you get from the speed and from the speed of the car. Either it's dissipated in the friction brakes, in braking resistors, or it's stored in the battery instead. But here, to remove the brake resistors, to downside the friction brake, if the battery is full and we cannot put the energy there, then we dissipate in the electric motors by really using them with very poor efficiency.
We have one other question in the audience.
Yes, I have another question for the project CEVOLVER. You were discussing about this navigation system that would integrate also the needs for the charging, so that the user could have better knowledge on where to charge, how to charge. And my question here is would this navigation system also be interconnected also with the charging network, so that the car or the vehicle will know when he will reach to certain destination where he or the vehicle should be charged? Is there the charging available? What is the queue? What is the expected time? What is actually the, let's say, the cost of charging at this location? This already smells a little bit about the CCAM, but I think from the point of view of the user, this could be very useful and efficient. Thank you.
Absolutely. I'm not 100% sure. Sorry for that, but I will collect, of course, and come back to you. No, this is the point I mentioned before, I think, related. It's also a question related to the business model, but with regard to the connectivity. Connectivity issues, as you probably know, especially in Germany with 9 border lines, could be difficult in case of near corners to the frontiers, so to speak. It's a question, for example, also of the, I only know the German term, Grenzfrequenzregulierung, which means the Bundesnetzagentur, the agency, is responsible for not facing cybersecurity attacks or so. So this we have to take into consideration by installing such a business case, which is absolutely valid. It's a very good question, because the cloud services for the charging infrastructure are the key for me, in my eyes.
Follow up a second on this. Of course, cloud service is absolutely relevant, but I think, and this is my problem, because I don't think you already implemented or addressed it in the project, and maybe it should be for the next 6 months. The operability and security issues linked to the OEMs that will have its own brand independent and anonymized cloud. So it's not only a problem of connectivity between member state and border, but it's also OEMs based.
Of course.
How do you plan to address it, or is there a way to address it?
Very heavy question for the end of this session.
there since morning, but I was waiting for a moment.
You were searching for me to answer.
As you did not been talking too much, I mean, we leave you the last 10 minutes.
Yeah. No problem. The problem is, in the end, I can't answer that question. I mean, this is a regulatory aspect, huh? When I remember a tricky regulatory aspect. I remember 5 years ago at the Vienna Transport Research Arena. 5 years ago already, there were guys from insurance companies, mainly in especially these sessions, and were answering your question, and not mechanical engineers or CCAMP related cybersecurity engineers or OEM manufacturers. So again, this is in the end, it's a political question for me. And
I can take it as an answer. Maybe not the most satisfactory, but be also interesting to see how you address it in the project.
Even
if you're just managing with one.
No,
OEM,
this is
correct?
this is a result. If you come to the project dedicated to SEVOLVER, we have to address that further on. This was my last slide. This is not finished, of course. This is an important point.
So I guess, are there any more questions from the audience? Otherwise, we have had a quite long Q&A session, I guess.
They're tired.
They're a little bit tired. So if there are no more questions, I think we can relieve them for today. And thank you for your endurance during this session.
If I can, big round of applause to the presenter, and thanks again.